Hi, my name is Daniel. I'm a PhD student at the Technical University of Munich, and today I'm going to present our work on build system-aware multi-language regression test selection in continuous integration. The work was done in collaboration with our industry partner IFAU Traffic Technologies, which is one of the world's leading providers of public transport software solutions. Before we go into the context of IFAU, I want to give a brief introduction into the research area of regression test selection. Regression testing is a regularly performed testing activity that ensures that introduced changes do not unintentionally affect existing system behavior. Say you have a program and a test suite, and you introduce changes to your program. You want to re-execute all the tests in your test suite and find any regressions that you perhaps introduced. The problem is that with growing test suites and limited testing resources, this becomes too costly. So executing every test after every change is simply infeasible. Regression test selection tries to identify the relevant test cases for the changes. So it tries to create a subset of the test suite and only execute that subset, but still detect all potentially failing test cases. Now let's have a closer look at the context of IFAU. At IFAU, there are 3 releases per year of the main software system, and developers create pull requests from their bug fix or feature branches to merge their changes into these release branches. Whenever they create such a pull request, a PR pipeline is created, and that PR pipeline looks as follows. As we can see, the monolithic code base is split into 2 parts. There's a C++ code base and there's a Java code base. And depending on what kind of changes have been introduced inside the pull request, the different pipeline steps are executed. So for example, if we have Java changes introduced, only Java changes introduced in our pull request, then only the Java related pipeline steps are executed. Importantly, there are many Java tests that are so-called long-running Java tests, and they use also dynamically linked libraries built from the C++ sources using the Java native interface and these cross-language links. So in case we have a change to the C++ code base, we still need to build the Java sources and run all these long-running tests. The problem with this is that even if we only consider the Java steps, we have on average 2 hours and 50 minutes for those pipeline steps to execute them. And this is a problem for developers because these feedback times are really long and they do not want to wait. And the second problem is that what we looked into in earlier work, unsafe RTS, is not really feasible in the case of release branches. Unsafe RTS is, for example, using heuristics such as when did a test fail for the last time, and if it failed in the previous, for example, 10 runs, then you might want to re-execute it. So it's not entirely based on, or it's not necessarily based on changes, but it's rather based on heuristics, for example, on the test history. But this is problematic if we miss any failures and the code goes onto the release branch, because the code could potentially be shipped to customers' code bases. Let's have a closer look at the code base at IFAU. It counts more than 30 million physical lines of code and is split into the 2 major parts I was mentioning, C++ and Java code. But there are roughly 19 million lines of code in mainly domain-specific languages, but also in other general-purpose languages and especially in non-code artifacts. Also, the code base is structured into thousands of Maven modules, which can be individually built and tested, and themselves are configured through XML POM files. Now, the problem with existing safe RTS techniques is that first, they are impractical for multi-language code bases. And secondly, they are unaware of build system or compile time dependencies. So say we have a change in one of the POM XMLs by for example, we replace a runtime dependency, existing RTS techniques will not take that into account. And therefore, we require a different approach for SEIP RTS. And here are the requirements that we collected. Firstly, it needs to be build system aware. What does this mean? Well, there are two aspects to that. The first one is existing RTS techniques. They typically use checksums, for example, of files to determine which files have changed and which tests that use that file have to be re-executed. However, in this case, to build a checksum of, for example, a class file, you will need to compile the Java file in advance. And compilation takes a long time at IFAU. It takes roughly 30 minutes, even though we have 96 core parallelization. And therefore, we only really want to compile or build what needs to be built. So these approaches for RTS are not really transferable to our use case here. Secondly, if there is a change in some build system configuration, as I said, these configuration files for Maven, for example, we want to consider that as well when we select tests for execution. So say runtime dependency has changed, we want to select all the tests that are potentially affected by this runtime dependency change. Secondly, we require multi-language awareness. I have already mentioned the cross-language links through the Java native interface and the different languages that are used throughout the test execution. So for example, XML files are accessed or SQL files are loaded. And we have to somehow take that into account when we build a suitable RTS technique. The same holds true for non-code artifacts. So as I said, there are non-code artifacts, for example, CSV files that contain expected test results, and tests then compare the results that they created against these CSV file contents. And we need to take that into account as well. This is the RTS technique that we propose. And as you can see here, in our work, we are focusing on optimizing the Java part of the pipeline. So before the Java pipeline steps are executed, there is our test selection technique here, the build system aware multi-language regression test selection. And there are several inputs and 2 outputs. Maybe let's start with the outputs. We output the selected modules, so those modules that need to be built. And we also output the selected tests. As an input, we have 3 sources of inputs here, and I'm going to explain in detail now what these inputs are. The first ingredient for the RTS technique is file-level multi-language test traces. So what is a test trace? A test trace, in our case, is the information, the set of accessed files during the execution of a test case. And we are borrowing from an existing RTS techniques that has used system calls in the past, this idea of tracing process and file system calls to determine which test is actually accessing which files during its execution. These test traces are obtained in separate CI pipeline runs. So every day there is a CI pipeline running for every release branch that collects these test traces. And here I have an illustration of what the tracing actually looks like for one sample test suite. So say you have one test suite, and in this case, this is a JUnit test suite. And this test suite is forced to run in its own JVM process. We can do this by running this Maven command that I've put here. By using system call tracing, we can analyze which processes are spawned by that JVM process, so by that test, and which files are accessed while the test is executing. And we can see here that there are several class files, a jar file, and a DLL file accessed. Now, there are 2 problems with this approach for tracing the system calls related to files. The first one is You can see it here on the right side. What if a jar is accessed? There might be several files packaged inside that jar, but we will only see a single access, file access issued to the operating system. And this is problematic because we might miss all the resources and class file that have been packaged inside this jar file. So in this case, we are instrumenting the class loader as well, and thereby we also find all resources that are accessed from inside jars. The second weakness is that we do not know what C++ source files are actually covered when a DLL is accessed. And for this, we use the compiler output from the Visual C++ compiler and create what we call DLL to source mapping. So knowing which sources are actually compiled into which DLL. The next step is the test and module selection. For this, we need to analyze the change set of the pull request, and by looking at the change set, determine what files that we could potentially find in the test traces are affected by the change set. There are different rules for different kinds of files. For example, for a Java file, we need to find out what are the potential class files that are compiled from this Java file, or that are generated by the compiler if this Java file is compiled, because those we can potentially find in the test traces. For all C-related files, we need to figure out what are the DLLs that are affected by the changes to these C files. And for the POM.XML, WSDL, and XSD files, we need to figure out what are the tests in the parent and the downstream modules of those modules that contain these files, and select those for execution, because potentially all tests could be affected by changes to the POM.XML, the WSDL, or the XSD files. In case of any other files being changed, for example, a CSV file, we simply add that file to the set of affected files. The next step is the selection of tests and modules. Firstly, we select all the tests by looking at the test traces and looking at the affected files that we collected from the change set analysis. Thereby, we can determine what tests have to be run. In the next step, we also need to figure out what are the surrounding modules that we need to compile in order to be able to execute those tests. And also, we need to look at what modules are directly affected by the changes, and those need to be executed, or those need to be built as well, similarly as you might know it from an incremental build system. This concludes the overview of our technique. To evaluate the technique, we performed an empirical study at IFAU to answer the following research questions. First, how much testing effort reduction can we achieve by selecting tests using our RTS technique? Second, how safe is it in terms of real missed failures? And third, how much end-to-end CI pipeline execution time can we actually save? Our experimental setup looks as follows. For the evaluation, we looked at 3 release branches from 5 weeks of development. The oldest release branch, denoted here by RV1, typically receives pull requests with smaller change sets. These are perhaps minor bug fixes. Whereas the most recent, or the current release branch, RV3, will still receive active feature development, so probably larger change sets. To answer research question 1 and 2, we deployed our RTS technique to release branch V1 and V3. You can see it here. But we still executed all tests. This way we can simulate how much testing effort would have been saved using RTS. But we still have retest all information. Note that we do not want to execute retest all and the selected tests from RTS, because this would induce, at the worst case, twice the overhead, and this is very costly. Next, to measure the actually achieved end-to-end savings in the pipelines, we deploy our RTS technique at release branch V2 here for 4 weeks and compare the measured execution time to the times at release branch V3 here, as they typically do not differ much. But to limit the threat of validity stemming from this inter-branch comparison, we also perform an intra-branch comparison. And for this, we actually run RTS in the 5th week of our evaluation period and compare the execution time to the 4 weeks before. This way, we minimize the risk of an evaluation bias while not having to execute both retest all and all selected tests for a single pull request CI run. Overall, we consider 5 weeks of development activity on 3 release branches and cover roughly 400 pull requests and roughly 2,700 commits. Let's have a look at the results for research question 1. What we can see is that the test effort reduction is quite big. We can see that we select on average 25% and 52% of tests, depending on the release branch. What we can see is that for older release branches, in this case RV1, we select fewer tests. And this is somehow intuitive because we have smaller change set and thereby naturally we can achieve bigger savings. We realized that test duration reduction of 72% and 42% respectively. And this is by looking at the test reports and the reported test durations. For research question 2, regarding the any missed failures, we looked at the 305 pull request CI runs where we actually observe failures that are undetected by our RTS. And we can figure that out because we still have the retest all information for these 2 branches. We then replay and manually inspect 50 randomly chosen CI runs with those undetected failures. And this analysis reveals that we do not miss any real failures. All the failures that occurred are unrelated to the changes inside the pull request. And they are coming from database misconfiguration on the one hand and flaky tests on the other hand. Still, there are some potential sources of unsafety, and they are outdated or faulty test traces because we are creating the test traces the day before we select on the next day. And also from dependency injection, which is an unsolved problem for RTS techniques. Other RTS techniques will also suffer this problem. Overall, our RTS technique did not miss any real failures in the evaluation, but there is potential unsafety due to the reasons that I just mentioned. Regarding the third research question, we find that depending on whether we look at the inter-branch or the intra-branch evaluation approach, we save on average either 50% for the inter-branch comparison or 63% for the intra-branch comparison. And this means that effectively developers will need to wait 50% less time than they have waited before. Maybe as a side note, the module and test selection of our technique itself takes on average below 3 minutes. And this is insignificant looking at the overall pipeline execution times. Let's conclude. So we presented and evaluated a novel approach for build system-aware multi-language regression test selection that selects modules and tests for compilation and execution respectively. We use system call tracing and static program analysis to achieve that. And our results show that we're able to reduce the end-to-end pipeline time for the Java part of the pipeline by roughly 50% or even more, depending on the evaluation scenario. Our RTS technique has been deployed and running on all release branches at IVU since September 2021. So this is really a practical solution that is also used in practice. I encourage you to read our preprint, and thank you very much